we get this general form when this function also has this parameter alpha and where limits are also some functions of alpha. Now if we differentiate this function, we'll get this first form, which is limits are same, and then we have this partial derivative of this function with respect to alpha dx, and then plus this form. Substitute x with upper limit into h dash alpha minus f g alpha into g dash alpha. So this is the general form of Leibniz rule of differentiation under the integral sign when the limits of integration are functions of the parameter. Now here the question is, we are given this function which is y equals 1 upon a, this integral from 0 to x ft sin a x minus t dt. Now we have to prove that d square y upon dx square plus a square y, it is equal to fx. Now we'll differentiate this function using Leibniz integral rule. Now here this parameter x, it is in the limits and is also in the function, so we have to use its general form. So here dy by dx, it will be 1 upon a, this integral from 0 to x, and then partial derivative of this function with respect to x. So it will be ft and then cos a x minus t into a dt. Now plus, now we'll put upper limit. So it will be 1 by a fx and it will be sin a x minus x and then minus. Now here lower limit is constant, so its derivative will be simply 0. Now here sin x minus x is sin 0, which is again 0. So we can write dy by dx as 1 upon a, this integral from 0 to x ft cos a x minus t dt, and we also have this a here. Now we'll differentiate it again with respect to x. So we'll get d2y upon dx square, and it'll be 1 upon a into a, and then from 0 to x. Now we'll partially differentiate it again with respect to x. So it'll be ft sin a x minus t, and then we have this minus sign here, and then a dt. Now plus, we'll put upper limit. So we'll put upper limit, a and a will cancel. So we'll get this as fx, and it'll be cos a x minus x minus derivative of lower limit will be simply 0. So this d2y upon dx square, it will be simply a square into 1 upon a 0 to x, and we'll take this minus sign out, and it'll be ft sin a x minus t dt, and here it will be simply fx, and cos 0 is 1. So we'll write this as fx. Now this 1 upon a, this integral, it is nothing but y. So we'll put the value of y here. We can write this result as d2y upon dx square plus a square y, it should be equal to fx, and this is what we need to prove. Now next questions, we are given this function f in which x is a parameter which is in limits as well as inside this function, and it says we have to find the value of f dash pi by 2. So we have to differentiate this function, and since there is a parameter in both limits and function, we have to use general form of Leibniz integral formula. So we can write f dash x as this integral from pi square by 16 to x square, and then we'll differentiate all this partially with respect to x. Now derivative of sin x is cos x, so it will be simply cos x into sin under root theta upon 1 plus cos square under root theta. Now plus upper limit. Upper limit will be sin x into sin x upon 1 plus cos square x into derivative of x square, which is 2x, minus derivative of constant is 0. Now we need to find the value of f dash pi by 2. So we'll put x as pi by 2. Now if we put x as pi by 2, here will be cos pi by 2, and then this integral from pi square by 16 to x square sin under root theta upon 1 plus cos square under root theta d theta, and plus sin square x will be sin square pi by 2 into 2 into pi by 2 upon 1 plus cos square pi by 2. Now cos pi by 2 is 0 and sin pi by 2 is 1 and cos pi by 2 again is 0. So we'll get f dash pi by 2 as pi, and that is the answer to this question.